Consider one turn of a rectangular coil of a length L and a width B carrying a current I. The coil is vertically suspended at the midpoint of PQ in a uniform magnetic field B direction, of which is taken as the x-axis. Y-axis is taken vertically upwards. We can write vector B as vector B is equal to B into cat vector I. Let us first consider the force acting on the element PQ of the coil. The force is vector F1 is equal to I into vector B cross to vector B directed vertically up. Similarly, the force acting on the element RS is vector F1 dash is equal to minus I into vector B cross vector B acting vertically downwards. Further, the forces modulus of vector F1 and modulus of vector F1 dash are also acting along the same line, that is, the y-axis. Being equal, opposite and collinear, they cancel each other. Now consider the element QR. The current along the minus y direction, so one writes for the current element QR minus I into L into j cat vector. The force vector F2 acting on QR is vector F2 is equal to minus I into L into j cat vector cross to I cat vector. That is equal to minus I into L into B into j cat vector cross I cat vector. That is equal to I into L into B into k cat vector. Similarly, the force acting on the element SP is vector F2 dash is equal to I into L into j cat vector cross B into I cat vector. That is equal to minus I into L into B into k cat vector. Vector F2 dash is in the negative z direction. Equations show that modulus of vector F2 is equal to modulus of vector F2 dash, and also that vector F2 and vector F2 dash are oppositely directed, but they are not collinear, so they give a rise to a torque. Viewing the coil from above, vector F2 dash, x-axis and vector A are seen. By definition, torque is equal to the magnitude of one force is modulus vector F2 multiplied by the perpendicular distance between the two forces is MA. MA is equal to B into cos pi by 2 minus theta, that is equal to B sin theta, where theta is the angle between the direction of the field and the direction perpendicular to the plane of the coil. That is equal to I into L into B into B sin theta. L into B is equal to A, which is the area of the coil, is equal to I into A into B sin theta. If the coil is having n turns, then modulus of vector tau is equal to n into I into A into B sin theta. Equation can be written now in a vector form as vector tau is equal to n into I into vector A cross vector B. The vector quantity n into I into vector A is called the magnetic moment linked with the coil and is denoted by vector mu. Therefore, vector tau is equal to vector mu cross vector b.